Swayam Prabha. Digital India. Educated India.
In the previous lecture, we discussed about the inelastic response spectrum, and in that we have seen that the inelastic response spectrum and the ductility, they are very closely related. In fact, the inelastic response spectrum is obtained for a particular value of the ductility. Then also we had seen that it is not easy to find out a value of your f bar y for a given value of the ductility factor mu, or in other words f bar y is equal to f y by f 0, and this is equal to inverse of the reduction factor. F 0 is the force or the resistance that is provided by a equivalent single degree of freedom system which is elastic, and F y is the yield resistance provided by the elastoplastic system. Both the elastoplastic system and the equivalent elastic system, they have the same stiffness up to the value of the yield strength F y, and that is how we defined F bar y is equal to F y divided by F 0. Inverse of that is called the reduction factor R y. So, the reduction factor R y means that the corresponding elastic strength in the SDF system, if it is divided by R y, then we get the value of F y or the yield strength of the elastoplastic system. For example, R y is equal to 2 means the elastic strength of the equivalent single degree of freedom system is halved for an elastoplastic corresponding elastoplastic system. So, F bar y and the ductility, they are closely related, and the equation of motion that you had written for the single degree of freedom system, it was in terms of the variable which is the ductility factor, that is in place of the displacement we wrote down the equation of motion in terms of the ductility factor. For a given value of f bar y, the ductility factor can be obtained by solving that single degree of freedom equation. Therefore, it is easier to find out the value of mu for a given value of f bar y. The reverse is of course not true, that is very difficult to find out the value of f bar y, in other words f y, that is the yield strength for a elastoplastic system for a given value of mu. So, what is done is that we solve the equation in which the ductility factor is the variable and obtain the values of mu for different values of f bar y which are assumed, and for a particular value of T n and the damping coefficient xi. In that fashion, one can obtain a set of values of mu corresponding to the values of f bar y for a given T n and xi. From that, one can interpolate the required value of mu and the corresponding value of f bar y. Once we get that, then that particular value of f bar y is again put into the equation of motion and we solve. Now, after solving, we get a value of mu, and if that particular value of mu is equal to the value of the mu that was interpolated from the set of values of f bar y and mu, then we say that there is a convergence. Otherwise, we continue an iterative process in order to obtain a pair of values of mu and f bar y which are compatible for a given value of T n and xi. And that is how one can obtain the value of the f bar y for a given value of mu. Now, once we get that, then from f bar y one can find out the value of f y, because f bar y is equal to f y divided by f 0, where f 0 is the strength corresponding to the purely elastic system, or in other words, for the same earthquake we find out an elastic response, and from that elastic response one can get the value of f 0. And once you get the value of f 0, then by dividing the f y divided by m 0, we get a value of f bar y, or in other words f y can be written as f 0 multiplied by the value of f 0. In that fashion, one can get the yield strength of the elastoplastic system, and we know that the yield strength of the elastoplastic system is equal to mass times the inelastic response spectrum acceleration. So, one knows the value of A, that is the inelastic acceleration response spectrum ordinate corresponding to a particular value of mu for a given set of T n and xi. Then by changing the combinations of T and xi, one can get different values of the acceleration, that is the inelastic response acceleration, for a given value of mu, and that can be plotted in order to get the inelastic acceleration response spectrum. Now, once we get the inelastic response spectrum, then from there one can get the inelastic velocity spectrum and also the inelastic displacement spectrum. So, the spectrums, inelastic spectrums that are obtained for a particular value of mu, they can be plotted in a tripartite plot. Also they can be plotted as an individual plot. They can be plotted in the tripartite plot because of the relationship that holds good between the inelastic response spectrum of displacement, velocity and acceleration, these relationship is the same as the relationship that we have observed in the case of the elastic response spectrum, that is Vy inelastic response spectrum of pseudo velocity is equal to omega times d, that is omega times the inelastic displacement spectrum response. Similarly, the inelastic response acceleration is equal to omega times the inelastic response spectrum of pseudo velocity. So, because this relationship holds good, one can plot the inelastic response spectrum also in a tripartite plot that was done for the case of the inelastic response spectrum. So, the a plot of the inelastic acceleration spectrum versus Tn for different values of mu is shown in this figure. In this figure, this m basically is wrongly written. In place of m, it should be mu, for it is mu is equal to 1, 1.5, 2, 4, 8 and so on. For that we have plotted Ay by g, that is the inelastic acceleration response spectrum ordinate is normalized with respect to the g value, and that happens to be is equal to Fy by the weight W, and where Fy is the yield strength of the single degree of freedom system. So, for a given value of mu and a time period t and for a specified value of damping, one can read from this ordinate the value of Ay by g and or the value of Fy, and this Fy can be obtained simply by multiplying m with Ay, and one can get the value of the yield strength corresponding to a particular value of mu. So, this is very important, because if we wish to design a system or a single degree freedom system for a particular value of mu, or say for example mu is equal to 2, then what should be the value of the yield strength. So, that value of the yield strength can be straight away obtained by multiplying the mass of the single degree system by Ay, that is the inelastic response spectrum of acceleration from this curve. For the case of multi degree freedom system, we will see how we can extend this and use these inelastic acceleration response spectrum for the design for an expected value of the ductility factor of 2. So, the use of inelastic response spectrum is the design of a particular structure for an expected value of the ductility factor of 2. So, this kind of the design spectrum is given in some codes where the response spectrums are provided for different values of the ductility factor, meaning that if those inelastic response spectrums are used for the designing the structure, then the structure is expected to have on an average or in an overall sense a ductility of 2 or 4 or 8 or 1.5 as the case may be. So, that is the use of inelastic response spectrum. Apart from that, the inelastic response spectrum can also be used for finding out the performance point for performance based design, in which a pushover curve, that is the curve of spectral acceleration versus the displacement, that is plotted for a pushover analysis, and the intersection point of the inelastic response spectrum for a given ductility, that gives the performance point. And this performance point shows that whatever base shear that we get from that performance point, for that base shear or the yield base shear, if we design the structure by distributing the base shear as a load for all the floors, then that particular structure is expected to give in an overall sense a ductility of mu is equal to the value for which the response spectrum was used. Now, the another important aspect that is derived out of this solution is the plot of f bar y versus the time period T n. We have seen that through an iteration procedure, one can find out a compatible set of a value of f bar y and mu for a given time period and a damping value. Therefore, it is possible to plot a curve showing the relationship between f bar y and T n for a given value of mu. So, such curve is shown over here. It is not m, these are all mu. So, they are plotted for mu is equal to 1, mu is equal to 1.5, 2 and so on. And the values of f bar y are plotted on this axis, and for a particular earthquake one can have a value of f bar y versus t depicted in the form of the curve would look like this. Now, this exercise was done for not only one earthquake, for several earthquakes, and then these curves were averaged out in order to find out a tentative shape of the curve showing the relationship between f bar y and a time period T n for a given value of ductility. The use of this kind of curve is that for a particular value of the ductility, if we have such an idealized curve, then using that curve one can find out what is the value of f bar y corresponding to a particular value of T n. And once we get that, then from f bar y one can calculate f y, or we know the yield strength for the equivalent single degree of freedom system. Now, that effort of finding out the curve for different earthquakes and idealizing them as a smooth curve led to certain formulation of f bar y, or the an equation for f bar y as a function of the ductility factor, and which are valid for different time periods. Now, here the T A, T B, T C, T D, T E, T F, they are the values of the time periods that we had considered in the case of the elastic response spectrum plotted in tripartite plot. The whole idea is to construct similar kind of plot or tripartite plot for inelastic response spectrum by looking at the variation of f bar idealized f bar y with Tn for specified values of mu. Now, once we look at these particular curve, we can see that for a value of T A is equal to 1 by 33, that is for very small value of T A, the value of f bar y is almost equal to 1, that is the T n being less than T A, the values are almost equal to 1, or in other words one can say that the system as if is behaving like a elastic system. From T A from T B to this will not be T C, this will be T C dashed. The T C dashed is shown over here in this curve. Now, for different mu's we can see that the T C dashed is varying, and between T B and T C dashed the variation of f bar y with T n can be represented by this, that is 2 mu minus 1 to the power minus half, or in other words 1 by square root of root over 2 mu minus 1. So, one can plot these lines from the T C dashed between T C dashed and T B, and wherever it cuts the T B axis, this point and this point they are straight away joined by a straight line. That is how we can get the curve, idealized curve for this segment as well as for the segment up to these points up to T C dashed. Then for T n greater than T C, that is this is the T C, for that the value of f bar y is given by mu to the power minus 1 or 1 by mu, and that is plotted over here for different values of mu, and this is extended and see the point where it cuts the T C axis, and those point and the point which we obtained here at T C dashed, they are joined by a straight line, and thus we get this segment of the curve. So, therefore, the full segment of the curve can be traced, and this shows the idealized values of f bar y for different values of T n for a given value of the damping and the ductility ratio mu. So, utilizing these relationship that is obtained from an exercise of finding out f bar y versus T n for a number of earthquake and averaging them, and from there trying to find out a relationship between f bar y and T n, some important output is obtained which are used in plotting the inelastic response spectrum curve from the elastic response spectrum curve. So, the idea now is to construct an inelastic response spectrum from the elastic response spectrum or idealized elastic response spectrum that we have obtained previously, and we had plotted on a tripartite plot. So, if you recall that how elastic response spectrum is plotted on a tripartite plot, then we will see that we require the values of the ground, maximum ground displacement, maximum ground acceleration and maximum ground velocity. So, they are first plotted in a tripartite plot, and that forms the baseline. Baseline, that is a line like this, straight line like this will go, then there will be a straight line will be going like this, and there will be horizontal straight line like that. Now, once we have those peak ground values, or the peak ground acceleration, peak ground displacement and peak ground velocity values, and there from that the baseline is obtained, then by multiplying those lines or the ordinates from that line by a factors alpha A, alpha B and alpha D, we obtain the elastic design response spectrum curve. And alpha A, alpha V and alpha D values are available for different conditions, that is for the extreme earthquake and for the design earthquake, and given in different literature. Now, once we have that elastic design spectrum, then the whole idea is to obtain the inelastic response spectrum from this elastic response spectrum. So, that is what we intend to do. The construction follows the following steps. That is, first what we do is that divide constant acceleration ordinates of the elastic response spectrum for the segment B to C by a reduction factor R y is equal to square root of 2 mu minus 1 to obtain the value of B dashed and C dashed. That is, here you can see that B C over here in the acceleration zone, the B C, that is divided by, these ordinates are divided by square root of 2 mu minus 1 to get this line, and this line obviously will be parallel to this line. Now, this is done because we have seen that the f bar y between T b and T c, that is given by square root 1 by square root of 2 mu minus 1, or in other words, the elastic strength is reduced by a factor of R y is equal to square root of 2 mu minus 1. The relationship between R y and f bar y, if you recall, is equal to R y is equal to 1 by f bar y. So, thus the value of the elastic acceleration is reduced by a factor of square root of 2 mu minus 1, and that is how this ordinate is equal to A divided by square root of 2 mu minus 1. Similarly, if we look at the value of the f bar y for a time period T n greater than T c, then it is the factor is 1 by mu. Thus, the reduction factor will be mu, that is the values of the elastic strength or elastic spectrum must be divided by mu. So, that is what is done over here in this spectrum. The velocity ordinates over here and the displacement ordinates on this side, or in the displacement zone and the velocity zone ordinates, they are divided by simply mu, and this also is divided by simply mu. So, we get the point over here on this time period line, and on this time period line, and on this time period life. And once we get that, then here at the end where the displacement, spectral displacement is equal to peak ground displacement itself. So, there also we divide the displacement by mu. That is how we get a point over here on this particular time period line. Then by joining these two lines, we get the inelastic response curve line between E dashed and F dashed. Here we assume that the value of the acceleration for a very small value of time period, they are the same, that is A and A dashed are the same. This follows from this relationship, that is Tn less than Ta, for that F bar y is equal to 1. That is why A and A dashed are the same. And after or below A dashed, the inelastic response spectrum curve and the elastic response spectrum curve, they are the same. So, in this way one can get the value of the inelastic design response spectrum for a specified value of mu constructed from the elastic response spectrum. So, therefore, if we wish to plot an elastic response spectrum and an inelastic response spectrum for a given value of mu, then the quantities that are required is the peak ground displacement, peak ground velocity and peak ground acceleration. One of those quantities should be specified, and if one of those quantities are specified, then the other quantities, other two quantities can be obtained from an empirical relationship that we have seen before. So, once we get the peak ground displacement, velocity and accelerations, then we obtain a baseline curve. From that baseline curve, one can construct the elastic design spectrum by multiplying the curves with the values of alpha A, alpha B and alpha D. These values are obtained, are available in different literature. So, using those values, then one can obtain the elastic response spectrum curve in a tripartite plot. And once we get that elastic response spectrum, then from there one can construct the inelastic response spectrum by dividing the elastic response spectrum ordinates by root over 2 mu minus 1 on the left hand side, and in the velocity prone and displacement prone regions the ordinates are divided by the mu value, that is the ductility factor values, and that is how one can construct a inelastic response spectrum for a given value of mu and a damping ratio. One example problem is solved over here. For a single degree of freedom system, an inelastic spectrum is obtained for mu is equal to 2 from the elastic design response spectrum, and the elastic design response spectrum, this was obtained in an example before, and from that elastic design response spectrum by dividing the ordinates by appropriate functions of mu, we obtain the acceleration, inelastic acceleration on part, then inelastic velocity sensitive region, and then inelastic displacement sensitive regions using the factors that I had discussed before. So, that is how one can get inelastic design response spectrum for mu is equal to 2, then mu is equal to 3, mu is equal to 4 and so on. mu is equal to 1, obviously will correspond to the value of the elastic design response spectrum. Next, the question comes that for the single degree of freedom system, all these things are valid in the sense that if we obtain a value of the Fy or the inelastic acceleration, then one can find out the value of the corresponding yield based shear corresponding to a value of a mu for a given value of mu. Now, if we analyze the single degree of freedom system, for that yield strength that is obtained from the response spectrum curve, the yield strength is obtained by multiplying m with the spectral acceleration value A, inelastic acceleration spectrum value, then one get the value of the yield strength, and with that yield strength if we carry out a nonlinear analysis of the system, then we will get the same value of the ductility for which we had obtained the inelastic acceleration spectral ordinate and also the value of the yield strength. So, this is true for a single degree of freedom system. However, once we are trying to use the same concept for the multi-story building, it is not possible to get a yield strength straight away for this structure for a specified value of mu because of the following reasons. It is difficult to obtain design yield strength of all members for a uniform value of mu. So, that simply thus for the single degree of freedom system we have got only one spring, or in other words one member, and therefore, the mu value and the corresponding the yield strength can be easily determined from the inelastic response spectrum curve. Since the number of members in a multi degree of freedom system are more than 1, therefore, it is difficult to find out the design yield strength for all members for a given value of mu. Next, the ductility demands imposed by earthquake on members widely differ. So, that is also another fact, because as the entire structure goes into the inelastic range, then different joints and different members undergo different inelastic deformations. As a result of that, the ductility for the individual members are different. Thus, there is no uniform ductility that can be talked about for the multi degree freedom system or a multi story building. Now, some studies on multi-story frames are summarized here to show how ductility demands vary from member to member when designed using elastic spectrum for uniform mu. This will not be elastic spectrum, it will be inelastic spectrum. So, using an inelastic response spectrum for a given value of mu, if you are wanting to analyze or find out the yield strength and analyze the building, then how the results are obtained or how the results vary from that of the single degree of freedom analysis. So, that is depicted. Building frames of sizes 5 story, 10 story, 20 story and 30 stories were taken as case studies. In that the frames are deliberately kept as a shear frame, so that the columns are only yielding. The time periods corresponding to the 4 frames are for the 5-story frame, the time period is 0.8 second. For the 10-story frame, it is 1.6 second. For the 20-story frame, it is 3 second, and for the 40-story frame, it is 5 second. 40-story frame is an example for a flexible building, whereas the 5-story frame is an example of a rigid frame. Now, the masses for the frames are kept as uniform all through, having a mass m at each floor. Now, the yield base shear for the frames are calculated using the inelastic response spectrum of the El Centro earthquake corresponding to a specified ductility factor. So, once the yield base shear for each one of the frames is calculated, then the base shears are distributed to the story shear, and this distribution is made as per the code provisions. This gave us the yield shear for each of the stories of the frame. Now, in order to perform the inelastic analysis, we need a backbone curve, that is a curve showing the variation of the shear force with the story displacement and showing the point of yielding, that is an elastoplastic backbone curve. Now, in order to provide that input, not only we require the yield shear for the columns, but also we require the stiffnesses for each of the stories. In order to obtain the stiffnesses, again we use the base shear approach for distributing the total base shear coming at the base of the frame, which is calculated according to the specified time periods and the damping. The base shear is then distributed along the height to find out the story shear as well as the lateral force that is acting at each floor level. Second thing that is used is that in order to make a convenience in the calculation, we assume that the drift for each story is uniform, which leads to a linearly varying displacement along the height of the building. Thus, the displacement described at the top of the building is enough to define the displacement at other floor levels. With these two assumptions, we write down the stiffness matrix for the entire frame in terms of the unknown stiffness coefficients for each floor, and solve the equation K delta is equal to P, where the P is the lateral loads that has been already calculated, which are in terms of M at each floor level. The matrix equation gives n equations with n unknown coefficients or stiffness coefficients. So, these unknown stiffness coefficients can be then obtained in terms of the story mass m and the top deflection of the frames, that is delta. Now, once we get the stiffnesses or stiffness coefficient of each floor level in terms of m by delta, then we use the stiffness matrix and the mass matrix, which is a diagonal mass matrix. So, using these two matrices, we find out the fundamental frequencies and the fundamental time period of the frames using the eigenvalue problem. Once we get the fundamental time period for each one of the frames, then we equate this fundamental time period with the specified time period that has been assumed, and this gives us a value of delta again in terms of mass. Thus, the entire stiffness coefficients of each floor can be now expressed as a function of mass small a or the mass of each floor. The yield story shears are also obtained in terms of mass, because the total story shear will be in terms of mass. So, thus now we can provide the backbone curve necessary for obtaining the inelastic analysis. With these backbone curves, each one of the frames are now analyzed for El Centro earthquake. The frames are now designed for a specified value of the ductility factor for which the yield based shear is obtained for each one of the frame. So, thus each one of the frame that is analyzed under El Centro earthquake is having a specified ductility factor. So, from the analysis we find out the ductility demand at each floor level, and these ductility demands obtained for each one of the frame are then compared with the ductility for which the frames are designed. The results of the study shows some interesting result. For example, for taller frames, the ductility computed or ductility demand that is obtained from the analysis are larger in upper and lower stories, and it decreases in the middle story. Secondly, the deviation of the story ductility demands from the design one increases for taller frames. In general, the ductility demand is maximum at the first story and could be about 2 to 3 times the design ductility for the frames. Thus, some increase of the base shear by certain percentage tends to keep the ductility demand within a stipulated limit. Therefore, if the base shear which is obtained by the response spectrum method of analysis and the base shear coefficient method, then the greater of the two base shears is better to consider in the design, and thus this can help in improving or thus it can help in meeting the greater ductility demand that is obtained at the first floor level. Let me now summarize what we discussed in this lecture. First, we described two systems. One is a elastoplastic nonlinear single degree freedom system and a corresponding elastic single degree freedom system. From that we defined the non-dimensional or normalized yield shear for the single degree of freedom system, that is F bar y, and a reduction factor R. We also defined the ductility factor With these three factors defined, we are able to write down the single degree of freedom equation and with the elastoplastic nonlinearity in terms of the ductility as a variable, and can solve the equation to find out the value of ductility for a specified value of f bar y. Now, once we do that, then utilizing those results, one can construct what is known as the inelastic response spectrum for a specified ductility. Now, the inelastic response spectrum is similar to that of the elastic spectrum. Only difference is that the displacement spectrum is denoted by the yield displacement dy, and then we accordingly define Vy, that is the pseudo inelastic velocity or pseudo yield velocity, and then pseudo yield acceleration, which is equal to omega n square dy. In order to obtain these spectrums, it is necessary that we are able to calculate f bar y for a specified value of mu, which is not possible to obtain straight away from the solution of the single degree of freedom equation. So, an iterative procedure is conducted in order to obtain the value of f bar y for a specified value of mu, and once we get that, then one can plot the f bar y or the acceleration, yield acceleration versus time period for a given value of ductility. Also, one can examine the variation of f bar y and time period in the log-log plot, so that one can derive some idealized equation which expresses f bar y in terms of the ductility factors. And once it is known, then we have shown that it is possible to draw an inelastic, idealized inelastic design spectrum from the elastic design spectrum. In this and finally, we have also discussed the inelastic behavior of the multi-story frame in terms of the ductility demand.